Once you've generated your code for your prime number detector, your even odd detector, your top VHD, your test bench, and your constraints, your file structure should look like this. There's the constraints, here's the simulation. Notice there's not a folder called syntax error, and there are no underlines that are like they would look like spell check as red underline something. If you have something like that, then you have a syntax error, and you need to look at your TCL console, your Tickle console, and your messages to nail those errors down. So one thing I want you to note is if you get one of these warnings, if you have to go to messages, I usually just unclick the infos here because I don't want to see those. I just want to see warnings and critical warnings and errors. Warnings that look like this are nothing to worry about. In fact, usually they'll just be your code will still work. If you have a orange icon that's a critical warning, that's a bigger issue, and especially a red error. Critical warnings and red errors will be showstoppers, but these yellow warnings are, it'll still run. They're not perfect, but it's good enough. And right now I'm running some student code that was sent to me to debug, so I've just got it to work for the moment. And what I'm going to try to do here is we've got to run the simulation and see what the results are. So when we're running the simulation, what we're doing is the top TB file is generating a counter that is counting from 0 to F over and over again, and then it's putting that number on our input switches. So once I have the output here, I'm going to click this button to float this window. It just undocks it, and then I'm going to use the zoom fit button to zoom out. I'm going to resize some of this. I still want to be able to read the text over here. I'm going to move counters up, and then I'm going to start zooming in. And what I'm zooming in for is I want to be able to see one full iteration from 0 to F on my inputs, and then I want to see what those outputs are. The simulation will force the input, but then just read whatever the output value is. And so this is what you would be taking a screenshot of for the paper. So again, generate this in such a way that you can see one full iteration, so 0 to F. And reading this is very simple. The inputs I'm going to leave in a numerical form. In the LED outputs, I'm going to click this button to expand those and show me each individual bit. So if you would remember, LED 0 is your prime number LED. If it's a prime number, it will light up. It will get a 1. LED 1 is your even number detector, and LED 2 is your odd number detector. This is what you designed up in your top schematic file, your top behavioral file, and it's also what you labeled in your constraints. So the way that you would read this is, let's click anywhere in here. The values of where this little cursor is are shown here, and you can also read them graphically. So the number 0 is not a prime number. 0 is even because this is a 1, and it's not an odd number. The number 1, you can read the values over here, is not prime, it is not even, and it is odd. So you could see each of those how they correspond here. Let's go to a prime number. So 3 is your first prime number, so it should light that LED. It is not an even number, and it is an odd number. So when you write your code and you get no syntax errors, that's like saying that you've used the rules of English to create a sentence. When you run your simulation, you're verifying that that sentence conveys the meaning that you want. And so we're verifying that this thing does indeed light an LED for the prime numbers between 0 and F, it lights an LED for all even numbers and another LED for all odd numbers. So it does in fact work as we expect. If you have problems with your implementation, then this wouldn't actually show what you expect. It would give you some weird values. Maybe a number that's not prime would light up as prime, an even number might just show up as an odd number on these LEDs. So you can go back in your code and debug it there. So once you've done your simulation, now you need to download it to the board. I usually close the simulation, this bar up here. You just click the X and it will close your simulation. Go back to your regular project manager. Now we need to generate the bit stream and open the hardware manager and download it. So generating the bit stream will run a number of things, and it will actually take you a good while to run that. It'll run the synthesis, implementation, and then generate bit stream in that order. Then we need to manually open the hardware manager. So the hardware manager is the thing that connects to the Basys board. But we're using Vivado in a virtual Linux machine sitting on top of my desktop Windows machine, or my laptop rather. So what we have to do is connect our USB from the Linux machine to the actual hardware. And the way you do that in VirtualBox is right click over here on this little USB icon and then select, these are all the USB things connected to my computer. I want to select the Digilent USB device. When you do that, if you have your system sounds on in Windows, you'll hear it disconnect a USB device from Windows and then reconnect there. So if I now right click this, I've got a check mark next to Digilent USB device. That means that now my Linux machine, and therefore Vivado, can talk to that Basys board. So I'm going to go to Open Target, and there's two ways to do this. If you click Auto Connect, it'll just automatically detect it. Recent targets will show you your most recent ones, and then we'll run this Open New Target just so you can debug it and do it manually if you ever need to. Usually you just want to do the auto detect is the best thing to do. If you have to, you go here, you just click Next, Local Server. That means you're connecting to something on this computer. Click Next. It will connect to your Basys board and detect it. Click Next and Finish. And now up here it says that you are connected to the Basys board and it gives you your info for it. And you want to click Program Device, and then this little pop-up here is the name of the chip that's on the Basys board. We selected that when we started our project. Now when this happens, a pop-up will show, and typically this will be filled out with the appropriate information. What you're going to look for is the top.bit file. Bit is the file format for the bit stream we're going to put on the machine, and the file path is kind of interesting. Sometimes this doesn't pop up already filled out. So the way that you get to that is you just click the File Browse button, and you're going to go to your project. So I'm on my desktop folder right here. My project is here, and then you're going to go to Runs, Imp1, that's implementation, and then top.bit, and that's the file we're going to download. And when I click Program, it's going to actually program my Basys board. And you can't see it because I don't have a camera on it, but it is in fact telling me even numbers, odd numbers, and whether or not they are prime. So that's all you need to know. If you have any questions, please email me and I'll be more than happy to answer as soon as possible.